MIT researchers have pioneered a new fabrication technique that enables them to produce low voltage, power dense, high endurance soft actuators for an aerial micro robot. The artificial muscles vastly improve the robot's payload and allow it to achieve best in class hovering performance. When it comes to robots, bigger isn't always better. Someday, a swarm of insect sized robots might pollinate a field of crops or search for survivors amid the rubble of a collapsed building. MIT researchers have demonstrated diminutive drones that can zip around with bug like agility and resilience, which could eventually perform these tasks. The soft actuators that propel these micro robots are very durable, but they require much higher voltages than similarly sized rigid actuators. The featherweight robots can't carry the necessary power electronics that would allow them fly on their own. Now these researchers have pioneered a fabrication technique that enables them to build soft actuators that operate with 75% lower voltage than current versions while carrying 80% more payload. These soft actuators are like artificial muscles that rapidly flap the robot's wings. This new fabrication technique produces artificial muscles with fewer defects, which dramatically extends the lifespan of the components and increases the robot's performance and payload. People tend to think that soft robots are not as capable as rigid robots. The researchers demonstrate that this robot, weighing less than a gram, flies for the longest time with the smallest error during a hovering flight. The researcher says that the take-home message is that soft robots can exceed the performance of rigid robots. The research has been accepted for publication in Advanced Materials and is included in the journal's Rising Stars series, which recognizes outstanding works from early career researchers. The rectangular micro robot, which weighs less than one-fourth of a penny, has 4 sets of wings that are each driven by a soft actuator. These muscle-like actuators are made from layers of elastomer that are sandwiched between 2 very thin electrodes and then rolled into a squeezy cylinder. When voltage is applied to the actuator, the electrodes squeeze the elastomer and that mechanical strain is used to flap the wing. The more surface area the actuator has, the less voltage is required. So the researchers built these artificial muscles by alternating between as many ultra-thin layers of elastomer and electrode as they can. As elastomer layers get thinner, they become more unstable. For the first time, the researchers were able to create an actuator with 20 layers, each of which is 10 micrometers in thickness, about the diameter of a red blood cell. But they had to reinvent parts of the fabrication process to get there. One major roadblock came from the spin coating process. During spin coating, an elastomer is poured onto a flat surface and rapidly rotated, and the centrifugal force pulls the film outward to make it thinner. In this process, air comes back into the elastomer and creates a lot of microscopic air bubbles. The diameter of these air bubbles is barely 1 micrometer, so previously the researchers just sort of ignored them. But when layers become thinner, the effect of the air bubbles becomes stronger and stronger. That is traditionally why people haven't been able to make these very thin layers. The researchers found that if they perform a vacuuming process immediately after spin coating while the elastomer was still wet, it removes the air bubbles. Then they bake the elastomer to dry it. Removing these defects increases the power output of the actuator by more than 300% and significantly improves its lifespan. The researchers also optimized the thin electrodes, which are composed of carbon nanotubes, super strong rolls of carbon that are about 1/50,000th the diameter of human hair. Higher concentrations of carbon nanotubes increase the actuator's power output and reduce voltage, but dense layers also contain more defects. For instance, the carbon nanotubes have sharp ends and can pierce the elastomer, which causes the device to short out. After much trial and error, the researchers found the optimal concentration. Another problem comes from the curing stage. As more layers are added, the actuator takes longer and longer to dry. They found that baking each layer for a few minutes immediately after the carbon nanotubes are transferred to the elastomer cuts down the curing time as more layers are added. After using this technique to create a 20-layer artificial muscle, they tested it against their previous 6-layer version and state-of-the-art rigid actuators. During lift-off experiments, the 20-layer actuator, which requires less than 500 volts to operate, exerted enough power to give the robot a lift-to-weight ratio of 3.7 to 1. So it could carry items that are nearly 3 times its weight. They also demonstrated a 20-second hovering flight, which is the longest ever recorded by a sub-gram robot. Their hovering robot held its position more stably than any of the others. The 20-layer actuator was still working smoothly after being driven for more than 2 million cycles, far outpacing the lifespan of other actuators.